So, hello guys, you're welcome to the last part of lecture one, and I think we made it to the last part. So, if you have been watching consistently, welcome to the last part, and I trust that it's been going well. And any questions you have, you can contact me on the office hour, student office hours. I'm going to give that information for you guys to reach out and contact. So, let's just go into it. So in this part, we're going to be doing properties of substances. And substances have their properties, and there are two properties, which is there are two major properties, because inside those properties you have other properties. So the first is the intensive properties. And the intensive properties, from the word in, you notice they are independent of amount and are used to identify substances. So it's not about the amount. It's not really, when something's independent, it means that it stands alone and not with the amount. It's not about the amount, it's about the properties of the substance. So it's used to identify the substance. Like when you see water, it's not about the amount of the water. Once you see water, you know it's water. There's some certain things that you have to see amounts to be able to say. So the extensive now is different. So this one is dependent on amount. So if it's dependent on amount, it means that you're going to be looking out for mass and volume. You want to look at for mass and volume. So the intensive and the extensive. Intensive, independent of amount. Extensive, dependent on amount. So the fundamental properties of matter is that it can be chemical properties, and these are properties that you observe during chemical changes that converts it to a new substance, basically. So when you mix stuff and then you see a reaction that is more chemical, so it's like reaction had to take place. You have to have reactants, and you have products, and then you have a reaction. So, and then the physical properties, this one can be observed without changes in the chemical identity of the substances. So certain physical, then there might not be changes at all, but you see a physical, because the word chemical means reaction took place. The word physical means that you're still not necessarily seeing anything, but there's an activity going on, but it's not necessarily resulting in a chemical change. There are certain things like that as well. So those are the fundamental properties of matter. And then the physical properties are your melting point and boiling point as the physical properties. And in this physical property, the melting point, for example, is the temperature where the solid changes to a liquid. So the word to melt means that something dissolves, right? Melts. It's like it was solid and all of a sudden it's melting. And heat is what causes things to melt. Heat is what causes things to melt. And actually, the drop in temperature is what causes the freezing. And I explained this before, that when molecules are frozen, they come together, the particles come together in a solid. Then when you put them in heat, you take away temperature, you increase the temperature. As you increase in temperature, you discover that the molecules will start going apart. And that's the first part of it, from solid to the liquid, is melting. And then the next part is, once you keep increasing the temperature, as the temperature, it now goes to the other third form of matter, which is the vapor or the gas. The gas. Don't want to use vapor, I was thinking of water. So it's the gas. And it's vapor and then the bubbles within the liquid, because actually evaporation, so it's from the word to evaporate or to vaporize. So you have those bubbles in the liquid. So notice that we talked about it. We said water is solid under special conditions, can be gas under special conditions, but it's liquid at normal conditions. So you see water around. So just those points, and it's a point. Melting point is a point at which you see that change. Boiling point is a point at which you see that change. It's not necessarily the phase itself, it's just a point. So we have gold. Everybody has gold. Everybody wants to get gold. Gold is a symbol for excellence, standard, gold standard. You talk about gold standard, and its symbol is AU. And talking about atomic symbols that we talked previously, you're wondering to yourself, how can you put AU? There's nothing A in gold, there's no U in gold. It would have been GO, but that GO is already taken by another element. So AU is from the Latin name Arium, so it's named AU. And then you have another AU. Silver too is you have another A, something that's different. Silver is AG, and the rest, and it goes on. So now look at density. So density is actually the ratio of your mass to volume. So it's like your mass over volume is density. And remember, we say the extensive property are based on your mass and volume. So mass and volume are the extensive properties, as we said earlier, but the ratio of mass to volume is an intensive property. Notice that ratio of mass to volume, mass and volume. So mass and volume, mass to volume. So ratio. So and it's basically density, because ratio of mass to volume is density. So calculating density, gases and liquids are independent measure. They independently measure the mass and the volume. And then the solid, you weigh this, you weigh the solid for mass, and then your volume is used by given dimensions. So you do for solids, you have dimensions, and then for the mass you weigh it. So that's how you acquire the measurements for mass and then the measurement for volume. So we have an interesting example here. So the example here is glycerol. Glycerol is a viscous liquid, and it's used for both pharmaceutical and food industry as a sweetener. I don't know whether some of you know what glycerol, but it's quite, you might have eaten it and you didn't even realize, because of some of the things they put in as a sweetener, as thickener and stabilizer. So to determine the density, the student delivers 15.0 milliliter sample by pipet into a flask with a mass of 28.45 grams. And notice that this thing is thick, so I give it up to the student that did 15.0 milliliter of that thick substance in a pipette. So he has to carefully suck it and put his thumb on it and transfer it into a flask of that mass. So the mass of the flask and the glycerol is this 47.37 grams. So what's the density of glycerol? That's the question. So I like you to attempt to solve it, given that you know that density is mass over volume. So you know what the volume is, you need to find what the exact mass of glycerol is, given the fact that you know what the mass of the flask is and the mass of the flask with glycerol is. So it's simple. So I've given you clues already from the way I'm talking, so I'm very sure you can quickly go right into it and solve it quickly. I'm very sure you can do it, so just try. Just go for it. You can do it. So just pause the video, do it, and then we'll continue. So pause right now. So I'm guessing you tried. Some of you didn't even bother, so let's just go for it. So we know what the masses of the MC is when you added it is. So basically we just minus the mass with glycerol minus the empty. So we find the actual value of the mass and then divide through. So it's straightforward. So when we minus that, we have the value. So we call density is equal to mass over volume. So we have the mass and then we divide it by the volume. So it's going to be grams per milliliter. So the grams per milliliter is the unit for density. So that's for that, and it's straightforward, very straightforward, just minus and then you divide. So the endpoint density is, and then the significant figure as well. So notice it was two significant figures, basically. It was in two significant figures. Not three significant figures, sorry. So some of the values were 4. So we go with the list, which is 3. So notice that that's a pattern now for us. So here you have an image just to show the density situation. Notice in the picture, some of you might see the wood on the surface, but you don't notice the ring underneath. And in your thinking, you'll be like, the wood is bigger, the ring is smaller, but how come the ring is in the water but the wood is on top? So density is what explains why. And I don't know, some of you might be from Jordan, some of you know the river Jordan that passes through, I think there's Israel and all those. So the river ends in a place called the Dead Sea. The river ends in a place called the Dead Sea, and the Dead Sea is known to be dead because there's no life form. There's no you don't have sea creatures, you don't have water, you don't have sea animals in the Dead Sea. And it's known also to be rich in salt concentration, so that if you're a very bad swimmer, you will float. You can't drown there, no matter how bad it is. And by the way, it's the same also for the sea. You can't float to a certain degree in the sea. You might be good at swimming in the sea, but when you get to the pool, you might look a little bit weird because there are differences. So when you add salt, an increase in salt content, there's a simple experiment you can do to confirm that. Your egg, if you boil an egg, peel the egg, if you put it in water, it will float. It will sink, sorry. But once you increase the salt content, add some salt into the cup or whatever it is you have that has the water, and put the egg in it, it will float. And that's an interesting experiment you can do to find out for yourself. There's one other one you can use you can find out if an egg is boiled or not. I do that trick with the students. I ask them, if I give you 2 eggs and I boiled one and I didn't boil the other, how can you tell without cracking the egg the one that is boiled and the one that is not boiled? And students give me very wonderful ideas and suggestions. And I don't know, think about it and tell me what you think. I don't know how you're going to tell me what you think, but just think about how you can, then I'll give you the answer. Okay, the way you can do it is the fact that one egg is not solid on the inside, so it means that there's a fluid inside it, and the other egg is boiled and it's solid on the inside, so there's a physics behind it. You try to spin the egg, you put the egg and spin it. The particular egg that has fluid in it will stop after a while, because if you try to spin it, the liquid balances off the spin very quickly, but the other one that is boiled will spin very rapidly and will spill for a long period of time. So that's how you can tell that an egg is not boiled or it's boiled. And sometimes you can use that to find out, because sometimes you can have a friend or a family member that just likes boiling eggs and putting them in the fridge, and then you try to crack it and find out that it's boiled. So that will come in handy someday. So that's for density. Now we move to solubility. So solubility is almost like the ability, on the word solubility, for something to dissolve. So the process by which a substance dissolves in another is basically what you call solubility. So the ability of that thing to dissolve is basically its solubility. So it's English language. Soli, that's solution. Ability to form a solution is your solubility. So it's ordinarily a physical change. So it's just physical. You put salt and water, it dissolves, and then you have a solution, which is a salt solution. So the resulting mixture is a solution, because we said from previous, I think that was the ending of lecture 1. We said you have a solute plus a solvent, mix them together, you have a solution. So it's like a formula: solute plus solvent, solution. So you have the solute and solvent react together, what you have is a solution. And if it's not liquid, metals come together, you have an alloy. So there are types of solutions. You have types of solutions. You have the saturated solution, the unsaturated solution and the super saturated solution. And the way I explain solution most of the times is like when you are hungry, you are unsaturated. When you're hungry because you don't have food in your stomach, so you're unsaturated. The word "un" is used to indicate not having something. So unsaturated is what you can be classified as. Then when you now eat something, you now become saturated. But when you eat and you can't stop eating, you keep eating and eating and eating and eating and eating, because some people, their breaks fail and they just keep on going because they don't know when they're going to see food again, which is a bad habit, but some people just do it once in a while. So when you keep doing that, you become super saturated. That means you're saturated. Super means above normal. Superman is in the air, so it's in the air, so it's above normal. So that becomes bad because you'll be wasting. Because most times if you put salt in water, and I think the seawater explains that to us, when you put salt in water, when there's too much salt in water, at some point in time you can be seeing the salt. You can be seeing the salt in the water, and it's almost like you're wasting the salt. Even with sugar, some people put too much sugar in their tea. Whereas some people start drinking a lot of tea, put too much sugar in the tea. Once you drink it, when you get to the bottom, it becomes very sugary. So that's super saturation. So I hope you saturation, unsaturation, and super saturation. So we have an example to explain, and sugar is the example that we use for this. Please pay attention to this question, because if you are not following, it gets confusing, because you have temperature mixed with mass and amount. So sucrose is a chemical name for sugar we consume. So it's called sucrose. There's sucrose, there's glucose, there's fructose, which is your natural sugar that you find in fruits. That's why it's called fructose, fruit. So it's soluble at 20 degrees Celsius, and it's 204 grams and 100 grams in water. So notice that the first amount is the amount of the sugar, the second amount is the amount of water that it can dissolve in. So at 100 degrees Celsius, you have 487 grams and 100 grams of water. So notice that when the temperature increases, you can dissolve more in it. You can dissolve more in the 100 grams of water, because notice that the 100 grams still remains the same, but you have more of the sugar dissolved in the water. Same when you're boiling water or when something is hot, the particles become very randomized, so you can do more in the heat than in the cold. That is why you better will dissolve your sugar in a hot tea than in a cold tea. Of which sometimes when it's too much, you see the residue underneath, which sometimes the sugar, and depends on the kind of sugar as well. Some of the sugars are very difficult to dissolve, so that's by the way. So the question now is, a solution is prepared by mixing 139 grams of sugar in 33.0 grams of water at 100 degrees. That is like the last. So the question is, what is the minimum amount of water required to dissolve the sugar at 100 grams? Notice the question is minimum amount of water, not sugar, and it says minimum. So this one is going to be hard, so don't pause the video for this one. Let's just do this one. We'll see another one later where you might have to pause the video for, so thank me later. So you have the values in comparison to the temperature, but we'll use the one for 100 because our question involves 100. The question basically is based off the 100. So the minimum amount is what is asked. We're given an amount. We ask for the minimum. So what we'll do is to relate the mass of water required to the mass of sucrose that is dissolved in 100 grams using the solubility conversion factor that we do have. So the mass of water required is what we're trying to get first, and how we get that is by the conversion factor, where we put the water, that of the water above, and then the sucrose beneath, where the sucrose will cancel sucrose, and then you have the amount of water that is required for the minimum amount. And then once we've done that, because the question is, if that is 31 grams of sugar and 139 grams of sugar and then 33 grams of water, what's the minimum amount of water that's required? So to do that, that was what we did here, where we take the sugar and then we run it against the standard, which is 487, sorry, I don't know why I'm calling 48. So it's 487 grams of sucrose. And then you find out that the minimum amount, and look at your answer. It was 33, that was the value there, but this is 28, which is actually minimum. So you have an idea when you put through your answers whether they really tally with what has been required. So the next question now is the maximum amount of sugar. Notice the word is maximum amount of sugar that can dissolve in the same 100 grams, in water at 100 degrees Celsius. So this is slightly different now. Now you're doing the reverse of what you did before, because you're looking for the maximum amount. So we have all of the information and then we're trying to work out the maximum amount of sugar. So try to do it, but changing the conversion situation so that you are taking the water to find the sugar, because before we use the sugar to find the water. So try it. I bet you can, because it's just to switch it up a little bit. So give it a shot, you can do it. Just pause the video and do it. You can. Okay, let's just go for it. Some people are just scared to death with anything about math. So let's just go for it. Mathematics is a stranger to strangers. It's a friend to friends. So just go for it. So you have 33 grams of water. I told you you're using water. Previously we used sucrose to find water. Now we're using water to find sucrose. So basically you just use the 32 grams of water against the constants that we're given as a conversion factor. So we just use that, flip this above and beneath, and discover that you have 161. And remember previously we had 139. So actually it's actually the maximum amount of sugar. So it makes sense. Makes much sense. So you have another example, 1.8, and this one is slightly different now because they said the solution is cooled out to 20 degrees Celsius. So the question is how much sugar will crystallize out? So it's almost like you cool it down, what amount of sugar will be left in crystal form? Because once you're cooling something, you're basically stepping down the temperature. And then remember, as I said, when you're dropping temperature, some of the molecules will be coming together to take solid form. If you increase the temperature, they'll be going out. So changes in temperature affects the phase of matter. So in this case, the sugar will kind of like crystallize, so it will form solid. Crystals are basically what you have when sodium, chlorine comes together to form crystal. Sodium is a metal, chlorine is a gas, come together, you form the crystal structure, and the metal gas come together to form crystal. So in this case, you have some crystallization going on the basis of change in temperature. So notice very closely that you are now going to be using the 20 degrees Celsius conversion factor for this. And since they said sugar, so you're going to use the water to find sugar, the mass of the water to find sugar. So try. I think some people can be good, some very smart students, of which everybody is smart. The only thing is that they don't just know that they are smart, but just give it a try and test yourself. If you get this one, then you can put yourself in the league of people that are very smart. Albert Einstein smart. So just try it and see. Just give it a try. I know, just try to work it out. You can do it, because from where we started to now, if you've been solving the questions, you're good. But if you haven't been, I still forgive you. find a place in my heart to forgive you. Okay, so let's go into it. So the strategy basically is to work based on the 20 degrees, and then you relate them through, and then you calculate and resolve. So this the gist. We'll just go into the main stuff. So we have 33 point, which is the initial mass of water. So you use that now with the conversion factor at 20 degrees to calculate the first. And when you get the amount of sucrose, then, and you find that that's the amount, then you work out the undissolved from the total amount that you have. It's like you work out the mass of water and find out the amount of sucrose that actually got dissolved, and then you go to the main total that is paired with 33 grams of water, and then you minus what you got from this, and then you have the amount that is undissolved. Does that make sense? Let me repeat myself again, because I know some people are already confused in their house and trying to wonder what exactly. So look at what it is. You have your mass of water, but this time you're using the conversion factor of 20 degrees Celsius. So you're going to put that into the conversion factor and then get the grams of sugar, and that is the exact amount of sugar that will dissolve in 33.0 grams of water. You have that out of the way. Then you go back to the amount that will dissolve in 100 degrees, sugar that will dissolve in 100 degrees, and then you minus the amount that will dissolve in 20 from the amount that will dissolve in 100 degrees. It's degrees I was talking about. So when you minus it, you have the one that didn't dissolve, and that is the one that actually crystallizes out on the basis of its cooling. So that's your answer. So I think if you didn't get it, just go back. It's a video, so just go back and play it again, and then it'll probably make sense to you. So that's it for this. We are done with it, and at the end of this chapter of this lecture, you should have been able to know how to convert Fahrenheit to Celsius and Kelvin is the only one that doesn't have a degree, and it's very much solid on itself. It doesn't have a degree, it doesn't even need a degree. And then you determine the number of significant figures, you can do that, and then you can determine the number of significant figures in calculated quantities. You can tell that, okay, when you have 4 significant figures, 2 significant figures, you always go down with the 2. And then the conversion factors, you should be able to convert things effectively. Celsius, Kelvin, Kelvin to Celsius, backwards, meter, centimeter, inches to meter. And also you should be able to you should use mass and volume, basically play around density, and then solubility, the ratios on solvent, solute to that of solvent. You should be able to work that effectively, because the idea is mass to volume. So you're doing mass, that is the solute, to volume, which is the solvent. So mass to volume. So basically that's it for this whole chapter, and know that you're going to have a homework or quiz around about this chapter. So the more you better understand it, the excellent you do in the quizzes. And every mark is important, every point matters, because people fail because they neglected the little things, such as watching this video again, understanding it. You might be like, oh, why do I have to, this is boring, just forget the boring part and look at yourself excelling well in the course, because if you fail, you'll come back again. And most of you are here again for the second time, or some of you, not most of you. Most of you are new students, so know that people can fail, not that they are failed, but they fail themselves. It's almost like they fail on purpose. So just try, give it your best, and I'll see you in lecture 2. So we have lecture 2 part 1 coming up soon, so look forward to it and learn this, understand this before you go for that. So try and catch up with the lectures. If it's online, if you're face to face, attend the classes face to face. If it's online, attend the classes online, and I trust you won't regret it, and you have an awesome time. See you guys. Bye for now.